Topic for this week pertains to how we can use samples to make inferences about populations. And in order to do so, we're going to need to draw on the notion of something called a sampling distribution. Let's say we want to use a sample to learn about a population. And for example, I might be interested in understanding, overall, how many people in the United States say that they support the death penalty. I can't ask every single person in the United States what they think. There's just too many of them. I don't have the kind of time or money. So instead, I'm going to rely on a sample, which I know should be representative of the population, assuming that I take a representative sample. My issue is that even with a representative sample, even with a simple random sample or gold standard of sampling, we can't assume that the sample looks exactly like the population thanks to sampling error. In other words, a sample gives us a best guess only. On average, overall, we expect our samples to resemble our populations, but it's always possible that random chance will create differences between the sample and the population that could throw off our estimate. So if we were to take a sample of 100 US residents and we find that 60 support the death penalty, our best guess would be that 60% of US residents support the death penalty. We know that our sample should resemble our population overall, so if our sample says 60% support, that tells us our best guess is that in the population, the number would be 60% who support. But we can't assume that exactly 60% of US residents overall in the population support the death penalty because of sampling error. It could be that it's a slightly different number, like 58%, and we just so happen to get a couple of extra death penalty supporters in the sample. It could even be that it's a really different number, and it's only 50% or 40%, but we got a really, really unusual sample, just by chance. And because we can't assume that our sample looks exactly like our population, we have to employ methods that will allow us to take this random chance into account. And so what we're going to be doing for the rest of this unit is using statistical methods to take sampling error into account to get an idea about how accurate or trustworthy our best guess is. In other words, we're going to be thinking about how to create a margin of error around our best guess that 60% of US residents support the death penalty, or around whatever other kind of value we're trying to estimate. And in order to do so, we're going to have to think of our sample as one of many possible samples that could have been taken. In order to do this, we're going to turn to another example. What you can see here on the slide are the names of people in this class and in my undergrad class this semester, and some very interesting, insightful, useful information about every one of you. Just kidding, this is the number of letters in your first name, as best I counted them on my fingers. So if you see any mistakes at this point, just don't let me know, because I literally counted on my fingers. But what we're going to do here is treat this data as data from a population. So we have a population of 61 students total, currently taking the class. And of these 61 students, we have data on letters of the name for everyone. We can also see the data reflected in the histogram. So we can see that the numbers go as low as about 3 to as high as about 10, and many people are somewhere in the middle. 5, 6, 7 was very common this semester. So our data here is a mean number of letters in a first name. And in particular, we're going to see what happens when we try to estimate the mean number of letters in a name using samples. So we'll start out here with some information about our population. For the 61 students across the two classes this semester, we have an average of 6.2 letters in a first name. So that's the mean that I found for these 61 names here. I added up all the numbers of letters, divided by 61, and got 6.2 for my population mean. But let's see what happens when we take a sample. So what you can see here in names in red is a sample of 5 students that I took from our overall population of students who are in the classes this semester. And this is a true simple random sample. I started out with a list of every member of the population, in this case the population of students across the two classes, and I used a random device to select names off the list. Specifically, I gave everybody a number from 1 to 61 in alphabetical order, and then I used a random number generator to pick names off that list. So our sample of 5 people here, Christina, Emily, Frida, Madison, and Malik, is a simple random sample of students across the two classes this semester. And if we calculate the mean number of letters across those 5 names, we come up with a sample mean of 6.4. The first thing to notice is that, look, this is pretty close to our population mean. We should expect a simple random sample or a representative sample to match a population mean pretty well, and it does here. But it's not exactly the same. It's 6.4 rather than 6.2. This means that just by random chance, we got a couple students with longer names than we would have expected, based solely on the idea that a sample should match a population. So we end up pretty close, but not exactly at the population value, which is what we should expect when we're dealing with probability. But let's see what happens when we take more samples. And specifically on the next couple slides, I've got 9 more samples to go. I actually did sit there clicking my random number generator. 5 times 10 samples, that's 50 times to populate these samples. So this is a true set of simple random samples here. Our next sample here, we get a sample mean of 6.0, followed by a sample mean of 5.6, 6.2, 5.8, 5.8 again, 6.6, 5.4, 6.6, and finally 7.2. So I went through those pretty quick because what I have here is a summary slide showing all of our different sample means. As a reminder, the actual population mean was 6.2 letters in a name. So we have a known population value that we can compare against. And our 10 sample means look like this. We had a value as low as 5.4, a value as high as 7.2. Some of our sample means were really close to what we'd expect, and we can see there that sample number 2 and sample number 4 actually gave us the exact population mean as well. But now you can imagine that typically when you're collecting a sample, you don't have a chance to collect 10 samples at once. And usually we have the time, money, resources, if we're doing research, to collect one sample, maybe 2 at best. And so when we're dealing with just one sample, we have one best guess. So if I got sample number 2 or sample number 4 for my samples, I would be spot on. My best guess would be great. I would have a really, really accurate view of what's going on in the population. But what if I only got sample number 10? In that case, I would considerably overestimate the mean number of letters in a name in this class. What if I got sample number 8? In that case, I would considerably underestimate the mean number of letters in a name in this class. And if I got some of the other samples, I would be close, but not quite right. So anytime we take a sample, we have to be prepared for the idea that there's going to be variation. Many of our sample statistics are going to be pretty close to our population parameters, do a pretty good job, but sometimes you will get an unusual sample, like our sample number 8 or our sample number 10 there, that's going to be a bit further off. Lucky for us, though, the characteristics of our sample means and the patterns of means that we see are going to also behave in some predictable ways. And this will allow us to take into account the sampling error. The first thing to note is that while we have variation across our 10 different sample means of 5 students each, what we'll see is that if we combine them, they all converge on a value that should look pretty familiar to us. And specifically, if we take the average of our 10 sample means, so add up 6.4, 6.2, 5.6, and so on, and then divide by our total of 10 samples, we get an overall mean that is very, very close to our population value. And in particular, we get a mean of sample means that is at 6.16 letters, which we could just round off to 6.2. So even though we have variation across individual samples, we get an overall mean of our sample means that is pretty close to our population mean. This is one of these properties of probability that's going to happen just about every time. If you take a whole bunch of different samples, you're going to see variation, but they will always converge. And when I say converge here, I mean if you take the mean of those sample means, they will always converge on the population value. Another thing to notice here is that while we had some amount of spread, and we went as low as 5.4 or as high as 7.2, we didn't have nearly the amount of spread that we had in the original population. So all of our sample means ended up being pretty close if we think of that relative to our original distribution, which went as low as 3 and as high as 10. And these two properties are going to be useful to us in thinking about what's likely to happen when we get a sample and how we can take sampling error into account. Summarize those ideas and make some more formal statements about them on this slide. So what we have here are graphs you've seen already. this is the distribution of our population values, and this is the distribution of our sample means. And these graphs represent two characteristics of repeated sampling. One is that if you take enough samples, the overall mean of your sample means will end up resembling the population mean. And that's what we saw here. We had an overall sample mean of 6.16, which very, very closely resembled our population mean of about 6.2. Another characteristic of repeated sampling and multiple sample means that you could calculate is that the sample statistics will have less variation overall than the original population did. In other words, they'll be less spread out than the original observations were. And we can see, again, both of these characteristics in this demonstration here. Our population mean ended up very closely matching the mean of our sample means, and we had much less spread in our sample means than we did in our original population. Another way of thinking about this is to say that when we take samples, the outcomes that we're going to get from our sampling are predictable. And we can predict both of these things about them. And as we'll see next, we can describe our predictions in even more detail in ways that will allow us to get pretty specific about what we should expect to see when we take samples. In particular, we can predict what we're going to get from a sample using something called a sampling distribution. And as you would have noticed or might have noticed on that previous slide, when you take a sample and calculate a statistic, some outcomes are more likely than others. We saw in our demonstration there that we tended to get values that were pretty close to that actual population mean. It was more likely to get something close to the population mean than far away from it. So when we start to talk about our sample statistics like this, we're essentially talking about the probabilities of getting different sample means. Some are more likely than others. We can describe these probabilities formally in something called a sampling distribution. What a sampling distribution lists out is all possible values of a sample statistic. So for example, what were all the possible means that could have been calculated from the different samples we could have taken from the classes, as well as the probability of getting each one. This might sound a bit familiar here. We saw in probability distributions in the last week that we could list out all possible values or all possible outcomes of some process and the probability of getting each one. Here we have all possible outcomes of our sampling process, aka all possible sample means that we could take, as well as the probability of getting each one. So a sampling distribution is essentially a probability distribution for some kind of sample statistic. And in this case, we've been looking at the mean as an example. We also know a bit about what sampling distributions look like. And this is where we're going to turn to theory, and in particular, a certain theorem known as the central limit theorem. Central limit theorem tells us that sampling distributions always have the same shape under a couple conditions. In particular, sampling distributions are always normally distributed, in other words, have that normal distribution bell curve shape that we saw last week, when one of two things is true. If the variable that you started with has a normal distribution, any sample will result in a sampling distribution that is normally distributed as well. In other words, the sample means will have the pattern of a normal distribution if you were to repeatedly take samples and record outcomes from those samples. The other situation in which we could expect our sample statistics to be normally distributed is when there is a large sample size. So if you have a sample size of 30 or more, and you take a whole bunch of samples and record a whole bunch of sample means, you could expect those sample means to follow a normal distribution pattern, no matter what your original population looked like. So when we introduced normal distributions earlier, I said they're going to be useful for two reasons. One is that they describe the natural world, and we looked at some examples of that. The other, though, is that they describe some important processes in statistics, and this is the big one for this class, where we can say that we know that our sample statistics, and going here with the mean as an example, we know that our sample means are going to be normally distributed. They're going to be most common around the center of our distribution, less likely to have something very low, less likely to have something very high, as long as we either start with a variable of interest that's normally distributed, or we have a large enough sample. So this is demonstrated visually in this little figure here, where we have on the top row a bunch of different populations that you might start with. One is a normal population, the others have different shapes. So this one's a rectangle called a uniform distribution, one is skewed, the other is just random or irregular. When we take small samples, like we did in the example that we just looked at with names, our normal distribution that we started with gives us sample means that are normally distributed as well. In other words, our most likely sample means were right here around where our population mean was, and it was less likely to get a really low sample mean, less likely to get a really high sample mean. For our small samples, though, we don't quite see the normal distribution when we're taking samples from these populations with different shapes. Looking at larger samples, on the other hand, we see a pretty noticeable pattern here. Our normal distribution, when we take a sample of 30 and then we plot out the different sample means we could get, we see our most likely sample means are still converging around this central point, which we know is going to be the population mean. And it's less likely you're going to get a much smaller sample mean, less likely you're going to get a much larger sample mean. What we can also see is that we get the exact same pattern for these other populations. So even for our uniform, skewed, and random populations, once we start taking large enough samples, sample sizes of 30 or above, we get the same pattern for our distribution of means. In other words, for any of these populations, we end up with sample means that tend to converge around the population mean, and it's less likely we're going to get a much smaller sample mean, less likely we're going to get a much larger sample mean anytime we take a sample. So we can describe a sampling distribution for means in pretty specific terms. Thanks to the central limit theorem, we know that it's going to have a normal distribution as long as the variable we started with is normally distributed or our sample size is larger than 30. And this means we know some other things about it as well. It will, like any other normal distribution, have a bell shape that is symmetrical around the mean. It will, like any other normal distribution, have a mean and a standard deviation, which is called a standard error when we're dealing with sampling and samples, that describe its shape. The mean tells us where it would fall on an x-axis or number line, and the standard error would tell us how narrow and skinny or how wide and flat it is, just like the mean and standard deviation for any other normal distribution. As you can see here in denoting the mean and standard error for a sampling distribution, we include a little x bar next to our mu for the mean and our sigma for the standard error, and this signifies that we're dealing with a sampling distribution of means, rather than a probability distribution of just individual values. Like other normal distributions, we can also say that the area under the curve between two values is equal to the probability of getting an outcome between those values. So the area under the curve between two sample means is equal to the probability of taking a sample and getting a mean between those values. Because of that, we can also apply the 68, 95, 99, 7 rule and find out the probability of getting a sample mean within 1, 2, or 3 standard errors of our overall mean. And we can also use z-scores or the z-table to find out the probabilities of getting sample means within different ranges. And as a reminder, standard error is the standard deviation for a sampling distribution. We saw in our lecture on normal distributions, in order to take advantage of these characteristics of normal distributions, to use the 68, 95, 99, 7 rule, or to find probabilities with z-scores, we need to know the mean and standard deviation, now called a standard error since we're working with a sampling distribution. And to find the mean and standard error for a sampling distribution for means, we're going to use information from the population we started with. We can determine the mean for our sampling distribution by looking to the population mean. We know that overall our sample means should converge around the same value as the population mean, so the mean for our sampling distribution is always going to be equal to the population mean. In other words, mu sub x bar, our sampling distribution mean, is always going to be equal to mu, our population mean. The standard error needs to be calculated from what we call the standard error formula. And the standard error uses the standard deviation from the original population as well as the sample size to come up with a value that describes how narrow and skinny or how tall and flat our sampling distribution is. So I'll go next to a quick example where we'll calculate a mean and standard error, apply the 68, 95, 99, 7 rule and z-scores, and find out some probabilities associated with sampling distributions. Let's now take a look at how we can apply the 68, 95, 99, 7 rule to a sampling distribution. What I have written on this sheet so far is a probability distribution that should look familiar from last week. This was the probability of obtaining a sentence of some number of months for an assault conviction in a particular court. Now what we're going to do is that we're going to imagine that we're going to take a sample of 100 people who received assault convictions in this court. And what we're going to be trying to figure out with our sampling distribution is what the mean of that sample is likely to be. If you were to ask each of those 100 people how long of a sentence they received and then find that average. In order to do this, we're going to need to fill in our mean and standard error on our sampling distribution. So our mean, we can write like this, where we've got mu and we have an x bar next to it to signify that we're dealing with a sample mean here. So again, we're predicting sample means. And our standard error, aka our standard distribution, aka our standard deviation for a sampling distribution, will be given using this notation right here. That's sigma with the x bar next to it. So we can fill in one of these values right away. We know that for any sampling distribution, the mean is equal to the population mean. So the mean for our sampling distribution here is 50. This tells us off the bat that if you were to take a sample of 100 people, ask each of those 100 people what sentence they received, and calculate a mean sentence, it would be very likely that you would get a value around 50. It's unlikely that you're going to have a mean that's much lower, unlikely you'd have a mean that's much higher. And this reflects the idea that in order to have a much lower mean, you'd have to just so happen to sample 100 people who had unusually lenient sentences, or to have a mean much higher, you would have to just so happen to sample 100 people who had unusually or unexpectedly harsh sentences. We can fill in the standard error, which tells us more specifically about the spread of this graph, using our standard error formula. And the standard error formula, if you recall, looks like this. Where we have our standard deviation, and we divide it by the square root of our total sample size. So as a reminder here, which I need a little bit more space for, but it's our standard deviation, this is our sample size. So with this in mind, we can identify these values, plug them in, and come up with a standard error for our distribution. So in this case, our standard deviation for our initial population was 10. And we have this information because we have it given here when we're looking at our probability distribution. So the standard deviation for our probability distribution was 10. The next thing we need to do is divide by the square root of our sample size. Our sample size is 100, and this is based on the idea that we're taking a sample of 100 people, calculating the mean for that sample, and then we're using this sampling distribution to try to understand what that mean might be. But we can plug that value of 100 in here for n. With this in mind, we end up with 10 over 10, and this comes out to a nice clean standard error of 1. Standard error will not always be a whole number. I chose this for this example because it's a little bit easier to work with. But the key point is that we're going to divide our population standard deviation by our sample size. But I'll fill this in here on my little diagram. We can see now the standard error is 1. So once we're at this point, we have a normal distribution with a mean and a standard error, aka a standard deviation. We can now do anything with this normal distribution that we could do with any other normal distribution, even though now we're working with sample means rather than raw scores. So let's say I want to figure out the probabilities of getting sample means within different ranges. So maybe I'm taking a sample of people because I'm trying to understand the workings of this court. Maybe I don't have access to all the records, and I want to get a sense for how far off my sample estimate might be if I take a sample of 100 people. So I'm just going to briefly redraw this a little bit bigger. Got our mean of 50, our standard error of 1. And to apply the 68, 95, 99, 7 rule, I'm going to mark off our 1, 2, and 3 standard deviation tick marks on the bottom. And sorry you just saw none of that as I was talking, but here it is. Drawn out a little bit bigger with our standard deviation tick marks marked off. Because we're working with a sampling distribution here, of course our standard deviation is called the standard error, and on the x-axis we're listing possible sample means that we could get. So my standard error in this case is 1. This means that if I
go out in my 1, 2, and 3 standard error jumps from the mean, I'm adding 1 to 50 each time to get there. So here I end up with 51, 52, and 53. So again, each time I do this, I'm adding 1. That's what my standard error is. I can do the same thing going in a negative direction, so here I'll end up with my mean -1, -2, and -3 standard errors going in each direction. So for each of these, I'm going to be subtracting 1 to get there. Again, because the standard error that we calculated from this standard error formula over here was 1. So I end up with 49, 48, and 47 as my -1, -2, and -3 standard error kind of tick marks or jumps away from the mean. So one thing to note quickly about this before I go into the 68, 95, 99, 7 rule specifically is that this is a much smaller spread than our original distribution up here, where we had tick marks of 10 months each, so this was 60, 70, 80, and 40, 30, and 20. So we said earlier in the lecture that a sampling distribution will almost always be more tightly clustered around the mean than our original distribution. If this thing were drawn to the same scale as the one up here, it would look something like this, right? Where our lowest value here is 47, our highest is 53, so this is actually, you can see that, a very tall, very narrow, very skinny graph in comparison, with our tails landing a little bit beyond 47 and a little bit above 53. But I don't draw things to scale here because it gets too hard to read, and I'm just not that good an artist. So we're going to go with this overall drawing, but note that it is more tightly clustered around the mean, as we would expect with this much, much lower standard error of 1. So now we can apply the 68, 95, 99, 7 rule. We know that we will always find 68% of the area under the curve within the mean and 1 standard deviation on either side. 95% within the mean and 2 standard deviations on either side, and 99.7 within the mean and 3 standard deviations on either side. Here, standard deviations are standard errors, again because we're working with a sampling distribution rather than a regular probability distribution. So we can apply this rule right here. We have a 68% chance of finding an outcome within 1 standard deviation or 1 standard error of the mean on either side. This means we've got a 68% chance that our sample mean will fall between 49 and 51 months. We've got a 95% chance that our sample mean is going to land within 2 standard errors of this overall mean on either side. This means we have a 95% chance that we're going to have a sample mean that lands between 48 and 52 months. Finally, going out 3 standard errors on either side, we can say that we're going to have a 99% chance of getting an outcome in that range. In other words, 99.7, a 99.7% chance that we will see a sample mean between 47 and 53 months. So now we have applied our 68, 95, 99, 7 rule, and we have a rough guide or a rough sense for what our sample is likely to give us. And where I think this is most useful in thinking about what we might get is that you could imagine, you're taking this sample of 100 people. Your goal is to understand what sentences are actually being handed out for assault in this particular court. And now we know that with our sample of 100 people, we have a 99.7% chance, so almost complete certainty, if we're not totally there, that our sample mean is going to be within 3 months on either side of the actual true mean. So based on this sample of 100 people we'd be taking, we would end up with a pretty good estimate, most likely, of what that true population mean was.
So let's say we wanted to calculate the probability of obtaining a sample mean within some range that is not directly specified by our 1, 2, and 3 standard error tick marks away from the mean. In previous weeks, we saw that we could have done this using z-scores. You could calculate a z-score corresponding to each of your sample means of interest. We could use the z-table to look up the area under the curve and to figure out the probability of getting outcomes between the mean and that z-score that you looked at and combine them in different ways in order to come up with our probabilities. That, however, is a lot of work. And in this point in the semester, we're going to move away from using the z-table or other similar tables, and instead we're going to see how we can do this on a quick online calculator as well. So what this calculator allows us to do is to obtain the probability of getting outcomes within some range of values. What we start out with here is the mean and standard deviation for our distribution. So I've already filled these in here to reflect our mean and standard deviation for our example data. We had a mean of 50 and a standard error in this case, since it's a sampling distribution, of 1. Let's say that we're interested in finding out the probability of getting a sample mean that is really, really close to our population mean. We want a really, really good estimate. So let's say we want to know the chances that we're going to get a sample mean that is between 49.8 months and 50.2 months. We don't want to be any more than 0.2 months away from our true population value. By filling these in, we can see the area under the curve corresponding to these two values becomes shaded, and we also get a probability. And specifically, we've got a probability of 0.1585, or about 15.9%, of getting a sample mean that's between 49.8 months and 50.2 months. If we were to take a sample of 100 people who had convictions for assault and calculate the mean sentence length received by the people in that sample. We can also use this calculator here to find some other values, so I'll get rid of these here. Let's say I want to know what's the probability that my sample mean is going to go too high. And maybe I have in my mind a value. I'll just pick one kind of arbitrarily here. What's the probability that I'm going to get a sample mean that is above 51.5 months? I can put this in for above. We can see the corresponding area becomes shaded, and we also have an area under the curve that corresponds to the probability. In other words, there's a probability of 0.0668, or about 7%, that I'll get a sample that has a mean of 51.5 months or above. Finish off here using what we just learned about applying the 68, 95, 99, 7 rule and finding probabilities using a normal distribution calculator. I'm going to ask you to find some probabilities associated with a sampling distribution. As you can see, this looks a bit familiar. We're going to imagine that we're going to be taking a sample from the probability distribution, the population that we were thinking about in the last activity. So we assume we have a probability distribution with a mean of 4.2 days and a standard deviation of 0.9 days. And we're going to take a sample of 36 jury trials and estimate the mean length of a jury trial based on that sample. So what I want you to think about and answer for this week is, A, does the central limit theorem apply? Why not? B, using the 68, 95, 99, 7 rule, what is the range of sample means where we have a 99.7% chance of getting a sample mean between those values? In other words, where are we pretty much certain that we're going to have a sample mean, in this range? And then C, using the normal distribution calculator, report the probability that your sample mean will be greater than 4.5 days. And what I'd like you to include with this activity is a diagram applying the 68, 95, 99.7 rule, like we did last week, as well as a screenshot or a picture of your findings using the normal distribution calculator. That's all I have for you guys this week, so as always, if you have any questions, please reach out, and otherwise, have a fantastic week.